Welcome everyone. Thank you for joining us for today's webinar on ruggedized lenses, where you'll be learning about 3 different types of ruggedization for imaging lenses and how they can maintain the optimal performance of your imaging lens in almost every situation. Before I introduce today's speaker, I'd like to go over a few housekeeping items. First, if you experience any technical difficulties during the presentation, please contact WebEx directly at 1-866-229-3239 or visit help.webex.com. If you have a topic-related question during the presentation, please type them into the Q&A portion of the WebEx control panel, which is currently being shown on your screen. In side-by-side mode, Q&A can be accessed via the top right corner of your screen. In full screen mode, Q&A can be accessed by hovering over the control panel at the top of the screen, selecting the down arrow at the end of the panel, and clicking Q&A from the menu. We have a team of expert engineers in the room to answer your questions in real time. And if we do not answer your question during the presentation, we'll be sure to get back to you individually following the webinar. Please keep in mind that this webinar is being recorded. A link to the recording will be sent to all participants after the webinar for your convenience. Now moving on to our presentation. It's my great privilege to introduce our presenter, Greg Hollows. Greg is the director of the Imaging Business Unit here at Edmund Optics and has 19 years of experience in imaging and vision technology. Greg began his career at Edmund Optics as an engineering technician and quickly moved up, now leading everything pertaining to imaging and vision for Edmund Optics. As a thought leader in the industry, Greg has authored numerous articles throughout his career on imaging technology, and he is a sought-after speaker on any optical technology. We're very excited and honored to have Greg with us today to deliver today's webinar on ruggedized lenses. So without further ado, I'm going to turn it over to Greg.
Thank you for the introduction. It's great to be here speaking with you today. As we start looking at things for ruggedized lenses, I do want to take a step back and just consider what has gone on over the years in the industry and why ruggedized lenses is an important topic for today. When we think about ruggedized lenses, they've actually been around for a long time, but what we've seen over the last 5 to 7 years, maybe a little bit longer, is a dramatic increase in the resolution of systems, lowering of cost in the sensor technology, and reducing pixel sizes. What this has meant is that imaging can go all kinds of places it didn't used to be able to go. Whether it's on the end of a robotic arm or into cars, into the field for military use, whatever it may be, camera technology and imaging technology is proliferating everywhere. But what that means is it goes into places that weren't used a lot previously, is that we're seeing new demands on the optics. And that just isn't from optical technology from a design or manufacturing point of view for making a good quality optic for good imaging, but also stability and ruggedization is required in a lot of these applications. And things like advanced levels of shock and vibration come up when you think of cars or vehicles or things like that. Wild temperature changes, things that are going into the field, can actually create all kinds of problems as metal and glass tends to expand and contract with different temperatures. And this can create issues. We're going to see a little bit about that near the end of the presentation, how that can come into play. And then also dealing with things as you go into caustic environments or difficult environments where you might have washdown conditions or contaminants, or just things, if you think about, again, for a vehicle, something that we all probably have in our lives that has a camera system in it now, going through a car wash, going out into the desert, going into the mountains, and maintaining good, reliable imaging throughout time is really, really important in those systems. So you see this coming up time and time again. So this is an area of increased need. But what I want to do is kind of baseline us with what standard products are available on the market today and give you an idea of what's going inside the optics right now for something you would buy off the shelf, and talk through some of the issues that would come up that would lead us to wanting to ruggedize a product. Most of the imaging lenses that are on the market today kind of look like the one that's in the upper right-hand part of the image here. It has a manual focus adjustment, manual iris adjustment to it. It has multiple threads in the barrel that when you move that focus adjustment, you can get a tremendous amount of travel range out of the optics, so you don't have to do long, tedious rotation of the focus barrel in order to get things in focus quickly. It also makes it so that things will move in and out without rotating, which is all very ergonomic and helpful for the average user who's going to be putting these into a standard application. Some of the other things that come into play that are really nice here, you get set screws on the outside that are going to let you go ahead and lock things down into place for a regular use application. And that's usually good enough for most things that are being done out there in order to make things be tight and held into place. But this is only one point of contact on a complicated mechanical mechanism to actually hold things down. The other things that are available on these sorts of products is a manual adjustable iris. This is made up of multiple leaves, and as you rotate the iris assembly, you'll be able to open and close that iris, which is really advantageous for trying to adjust things like depth of field, light control, aberrational control, things like that. Let you set to specific f-stop that you require, and again, this will use things like you see in the bottom image there with the thumb screws that are on the side of the lenses to lock things in place. The lower left image, you'll see that's actually what an iris looks like when it's separated from the mechanical housing, and you can see the leaves exposed there. It has a spring in there and some other things to make it easy to adjust and hold in place. There's lots of things going on in there that have moving parts. Problem is that all these mechanics can have sensitivity to shock. If you bang them or drop them or whatever it may be, they're going to have a tendency to move. If they're in a high vibration environment, over time, eventually, things like set screws can loosen, or just even simple shifts in place of all these mechanical mechanisms, if they come to rest or just adjust a little bit, can be a problem. The other thing you'll note here too is the optics are held in place by a retaining ring and different spacers, but there has to be give. There has to be room when you're assembling these sorts of products together to let everything fit when they're being put into place. But as things vibrate and will move over time, you can get subtle shifts and changes in the actual positions of the optics in the barrel, and that can create problems as well. So we'll see how that can affect things in a little bit. So moving on from the standard products, we want to look at the different types of ruggedization that are available. At Edmund, we have 3 distinct types of ruggedization that we're going to discuss today. First one is industrial ruggedization. This is kind of the next step up from the standard products, and you're going to see how this is highly beneficial in many ways and can get us over the hump in a lot of applications. It's a very straightforward way of doing things, and we'll talk about that in the next set of slides. After that, we're going to talk about ingress protection ruggedization. This is about getting around contaminants, particulates, vapor, things like that end up in some more caustic environments or situations where you have washdowns or things like that have to occur. And the final one is stability ruggedization. This is kind of the ultimate way to lock things down into place and guarantee the actual performance of the system and make sure it's working to the utmost level of repeatability. So let's start off with industrial ruggedization, and what I want to draw your attention to is the image again in the upper right. It looks a little bit different than the one we saw 2 slides ago. And what it has is the same optical setup in here, but we've made some distinct differences in this that allow for things to be made more robust when you're getting into a shock or high vibration sort of environment. First thing it's done is simplified optomechanics. They allow you to reduce the amount of moving parts that are in the system. Really what you want to do when you're building up a ruggedized lens is get the amount of parts that can actually move to a minimum. In this case here, you'll see that there's a pretty straightforward focus mechanism in the system that is a single thread that goes into a barrel that can be used with a lock nut or other locking mechanism, a clamp, something like that, or using several set screws, where before we saw something that just had the single thumb screw. Now in this scenario, you can have multiple set screws that are going in place to be locked down to actually clamp it from multiple positions. This will guarantee a much more rigid approach to focus change. And the single thread that's going through there is much finer thread. It requires a lot more adjustment, but it also means there's less room to move and actually adjust the lens system if there is any sort of change over time. The other thing that it employs, if you look at where it says aperture stop and the arrow pointed to the right-hand side of the lens, you'll see that it's actually the iris that we had before that had the multiple leaves and moving parts has been replaced with a fixed piece. This means it cannot change in size or position, which eliminates issues with if an iris in a standard lens was to shift position or open up or close at all. You would change the light levels, you would change the depth of field on the lens, and that can adversely affect whatever type of inspection you're trying to do. So this sort of setup is highly advantageous for guaranteeing those things don't change very much. Those 2 areas together allow us to get through putting things into vibratory environments and get a much more robust and reliable sort of optical system running with the camera and the software that you might be using. Another benefit of this that's not really part of the design, but it is a fallout piece of it, is that with removing those mechanical parts and all the complexity, you can build a much simpler system. And in the long run, this will actually reduce costs, sometimes significantly. In many cases, the complicated mechanics can add 20, 30, even 50% cost, depending on the lens design. As we look at things that are continued here, there are some disadvantages to this sort of setup, though. Compared to the regular lens that's bought off the shelf with a lot of flexibility to it, these lenses are going to be a little less ergonomic when you're focusing, and you're not going to be able to change the f-stop at all, so that can be a drawback if you're going to use them straight out of the box. Also, the focus travel may not be as smooth because of the way it's designed as a standard lens would be, which can be off-putting, but it really doesn't change the actual quality of the lens because the lenses that are being used here is the same optical design, so thus you'd be getting the same performance. However, most of those disadvantages are mitigated to some extent because what you would do is you would start off using a standard lens to benchmark your system, establish focus, understand whether that lens is going to work well enough or not for you, as well as setting the iris position and being able to document that to say, here's the F number position for the light throughput and depth of field that I require for my system. And then once you're done with that, you can shift over to the fixed version, this industrialized version that you would put into your machines long term. Some of the application spaces that these will go really great is areas like high vibration environments on a factory floor, things like looking at parcels or packages on a conveyor system, like the bottles we saw 2 slides ago. Vision-guided robotics is another great area for this because they can have situations where you have the camera moving back and forth and you have accelerations and stops and starts that are constantly going on. This will allow for things not to shift in position very much and actually perform very well for what you're trying to do. The other place would be where you're going to be deploying a lot of cameras that are under a fixed situation, same focus position, same F number position over and over and over again. You know you're going to do 50, 100, 1,000. You'd be able to actually get your costs down even more by using a product like this. And the nice extra bonus that comes with that, with the simplified design, these become more tamper-proof. In many cases, people will go in with the best of intentions to try and make an adjustment to the system to make it work better, but you might have it in a fixed position that's required for you. Removing the ability to do easy focus or easy iris change will allow this system to be much more robust and ruggedized against tampering or changing the system after you've installed it. The next area of focus that we want to look at is about ingress protection. This is a type of ruggedization which is similar to the last ones that we looked at, but it's really designed to prevent moisture and debris from getting in the inside. So if you look at the image in the upper right here, you'll see that these lenses are here with that simplified focus. It doesn't even have the ring on it in this case that would lock things down. There's no iris, so it has that same sort of fixed set of optics, but you'll notice the O-ring seal that's shown there. Using O-rings or RTV silicone is a great way to seal these lenses up to guarantee things don't get inside. You can seal one end, both ends, depending on the setup, and this will keep you from having things like moisture getting inside, which can lead to humidity and droplets getting inside that will actually deter from the image coming through clearly in the system. The bottom right image, you'll see that is a sample of a backup camera in an automobile. And in this situation, you know, you're going to be outside. You're going to have water spraying on it, rain, things from car washes, just general dew and precipitation. Other things that can get in there is dirt, dust, FOD, all those things like that that you want to guard against. So having this sort of protection in the system really goes a long way to solving many problems that can come up from things that are uncontrollable after the system is deployed. Again, it has the same set of simplifications as the industrial ruggedized lenses, so we have similar disadvantages to it. But in many cases, those things kind of go away a little bit. You know, while those disadvantages are there regarding the lack of flexibility, often it's not an issue because these are going into higher volume application environments. If you're going to go start with a lens at the simple level, the off-the-shelf design, work your way through it, and then lock these in later with all the specifics that you need, you can usually get around those issues. As you can see here in applications where you're going to be in food and bev, where it's going to be washed down, this can come up, or with the proliferation of autonomous vehicles and drones, things like this are really, really important. One of the benefits of something like this is in many cases, you would actually build another system around it to keep the liquid or the dust or whatever else is out of the system or contaminating it. But in many cases, those things add weight, size, and other problems. If you're going into a car or a drone like you see here on the right, you're going to want to be able to eliminate that extra weight, that extra sizing. Having lenses like this that can be ruggedized and not have to require an extra layer of protection can be highly beneficial. The other thing to keep in mind with this is getting around just things that are like that spray and that wash down, like we said before, can be really, really important. You know, dust and other things can come into play. But the biggest thing that you get out of these is that space-saving requirement. The last area that we want to look at is, and this is where we're going to probably spend the most of our time here today, is in stability ruggedization. So many applications have come up nowadays that require this, and this has really been driven not only by the desire to have things that have high levels of measurement accuracy, but when we see where things have gone in the sensor technology space, we've seen pixels reduce in size tremendously. If you go back about 15 years ago, the normal pixel size was about 9 microns in size. If I wanted to keep 1 pixel of measurement accuracy in my system, basically XY shift or pointing of my optics in relation to my pixels, I have about 9 microns to work with. And that's not a lot, but for a lot of systems that would go fairly well. We've seen pixels reduced down in size in recent history to approaching 1 micron. That's a 9 times reduction in the amount of tolerance you can have for misalignment of the optics in the system or shifting over time. If you think of it in 2 dimensions, the total area of that pixel has been cut by 81 times. That's the pointing accuracy that has to be held here. The level of stability that's needed to do some of these applications is really, really important when we think about that. I'm going to spend some time going through here how you deal with that and adjust for these things and things you have to keep in mind. The upper right-hand image, we have that same set of optics again. Looks similar to the industrial ruggedized design, but there's quite a few changes that have been put into place here to guarantee the performance that is going to be needed for these high stability environments. One of the biggest things, as I mentioned a little bit about, is they're designed to maintain optical pointing and positioning of the lens after shock or vibration and temperature changes. So shock and vibe, I think most of us are used to. This is the rattling or the dropping of a system or it quickly accelerating and decelerating, but temperature change can be an issue as well. As temperatures rise and fall, and this all depends on when things are installed and calibrated versus the high-end temperature that it might experience in a factory environment, you might see 10, 20, 30, 50 C change in the system. That can be critical to the actual alignment of things. When the lenses are assembled together and locked down and put into place, the optics are in one position. If they're put into a system and calibrated, they're probably pretty still close to that position. But as you have wild temperature changes in the aluminum or the other metal materials that are holding the optics in place change in size and dimension, you will have the opportunity for those optics to shift around. And what that'll lead to is a lack of pointing accuracy. When we think back to the pixel sizes that are on the sensors, and we're trying to hold 1 or 2 microns of shift, that can be enormous for the beam pointing. We're going to see some more about that in the final slides of the presentation, but that's something where temperature can come into play and become a real issue. Again, with these lenses, there's a fixed iris and a simplified focus use, just like the industrial ones, employing that same sort of concept to get us that first step down the line. But what else is also used here is 2 things that are in addition. First is an advanced focus locking mechanics. What this allows us to do, where with the standard lens you would have the 1 point with the thumb screw, with the industrialized lens maybe you could go up to a lock nut or 3 screws to actually clip in on all sides to get a more robust and tighter fit. This actually uses a clamping mechanism that goes around after the lens is focused and gets a 360-degree pressure placed on the lens so that it will not move position. This is the most robust way to guarantee that the mount and the lens do not shift position in relation to the camera. This is a huge increase in things. It adds a little bit more complexity. When you look at the lens system on the right there, you'll see in the light gray on the right-hand side this more complex locking mechanism. And if you look at the top part of that, you'll see a small circle. That is where the set screw goes in to create the clamping that's going on there. Positioning of that set screw so it's easily accessible isn't always done very effectively depending on the system. So this is something you want to consider before you build out the mounting or enclosure parts around the camera so that you can actually access it, so that after you focus the lens you can lock it in place. So there are some extra things to be kept in mind here when using that sort of level of clamping for that sort of ruggedized lens. The other thing that's a really huge player in this and helps get around the thermal issues, if you'll notice the 4 positions where there are spots that say glue on the upper right-hand image. You'll see 3 across the top and 1 at the back. These are all holes that are drilled into the lens housing where glue has been placed inside that allows for all the optics and the spacers to be tacked into place. Now, if you looked at the outside of the lens barrel, this might have those holes on 3 or 4 positions going around the outside, depending on the level of ruggedization and the glue that has to be used. And this allows you to have 360-degree holding of the optics inside the barrel itself, so they will not shift with vibration or heat and temperature change. So between that extra mounting clamp on the outside getting you aligned and stable to the actual sensor, and then the glue that is holding the optics in place, you have an extreme level of ruggedization that's going on. What you really get down to at the end of this is when you do all of these things, it allows you to guarantee when you put your optics into place that things are going to remain centered with that center pixel in the system once you've calibrated it. An example that we have here is this 3D metrology system on the end of this robotic arm. So you're looking at metrology and vision-guided robotics being combined together to do measurements. We're going to see how this could have problems without a ruggedized lens in a moment. But first, I want to step us through some of the applications that take place in these systems to show you where they could be used. And you can imagine some of them very popular ones out there in autonomous vehicles. When I think of a car or a truck riding across our roadways being driven by not a person anymore, but by a computer system and vision systems, and the amount of shock and vibe that I feel when I just take a trip with my family going down the roads, having lenses that I know are going to be tacked in place and controlled very effectively is comforting, and it helps the system perform at a higher level. We talked about the metrology system a little bit. I'll get back to that in a moment. But other things in just general vision guided robotics and even avionics and defense applications come into place where you want these things to be in the exact accurate position if we're going to be making decisions about how to move things around, whether it's in a manufacturing environment or to protect us. Making sure that we're looking at and focusing at the right things is of critical importance. But there's another application out there that really comes into play when you start talking about shipping systems around our instrumentation. When you look at this one, it looks like general transportation, maybe autonomous fork trucks and things like that. But what I'm referring to here is the actual shipping of the systems out to a factory floor environment. Systems are built up and in a laboratory environment, they're calibrated out, and then they're placed on a pallet, picked up by a forklift, dropped onto a truck drives across the country, another forklift picks it up at the other end, drops it onto the factory floor. Each one of those times there can be significant shock, and sometimes it's the highest level of shock that's actually experienced by the optics in the vision system across the board. This is a place where having those optics that aren't going to move around a lot from that calibrated position is of critical importance and needs to be considered, not just the situation of the application where the instrument is going to be used. And you need to have optics that are commensurate in terms of their ability to withstand shock and vibe in this environment, not just the one for the application of use. So let's look at stability ruggedization a little bit further as we wind up the webinar here. What I want to look at is the standard lens versus the ruggedized lens. And we're going to spend some time going through here and looking at a number of slides for positional accuracy and what happens when things are vibrated between these two lens systems. And we'll be able to see as we step through these images how optics shift around in one and not in the other. What I want to do now is we're going to show some images on that, but the one on the top in each one of these will be representative of the lens that is the standard off-the-shelf system. The one on the bottom will be is the ruggedized lens that we will see. As we step through here, what we want to look at is we're looking at this object. It happens to be EO in this case. It's going through an imaging system, and it's going onto a sensor. As you can see in both of these at this fixed position where there's no vibration going on, you'll see that the EO logo is in the center of both of the images on the screens in each of these setups. What I want you to notice as I click through these images that you'll see the optics moving around on the top one as the vibration is occurring, and we're actually getting shifting of the focus position on the sensor itself and moving the EO up and down. On the bottom image, they will stay in place because the optics are not moving. As I click through here, you'll see as I go from the first slide to the next one, we're getting some movement in the system. The optics in the top, if you look closely at your screen, you'll be able to see the actual blue optics in the barrel moving and changing position. You'll see that as that happens, I'm getting a pointing accuracy issue where the EO is flowing through the optics, but it's actually being aligned to a different part on the sensor. You'll notice on the bottom of the top image, on the video screen that's being shown there, the EO is moved from its ideal place and location. So if you're trying to do a measurement or a relative position in this setup, you will not be able to maintain that. Imagine for a second you have a metrology system that's looking at the center pixel, moving a robotic arm with that metrology system on it to find another center pixel somewhere else, but the center of the image is actually moved because the optics are sliding around inside the barrel. This could be microns, tens of microns. That could create huge problems when you're trying to get a guaranteed measurement out of one of these systems. You notice the one on the bottom, as things have moved or vibrated or been accelerated, nothing has changed, and we've kept that maintained position. This is partially because of the gluing of the optics in place and the clamping that is going on the outside of the system. I'm going to slide through here and let you see this kind of stop action movie that's going on to show how things are moving around. You can see the EO logo on the top is moving up and down. On the bottom, it's staying in place even though the whole system is moving in both of these setups. Let me slide through all these so that you can see that continue to happen. From this, it's pretty obvious why you'd want to go up to one of these stabilized, controlled, ruggedized imaging lens solutions for your system. This is really beneficial for the setups to make things happen in a way that is going to guarantee the accuracy and reliability of measurements Or long-term, as those optics do move around in systems, this can create problems with not just the beam pointing and the accuracy of the system, but as those optics slide back and forth, and even though it's only a little bit, you eventually can wear the optics down and create more vibration issues, dust particles inside from the glass, other problems like that that can actually degrade the imaging system and the long-term quality of the image that's being obtained. In conclusion, there are many different options for ruggedizing lenses. Really what you need to do is step back and understand all aspects of the applications you're trying to do, not just the end application, but as we mentioned earlier, the transport of the products, the installation of them, whatever might be going on, to guarantee that all of those things are taken into account, that you go to the right level of ruggedization. Now, one of the easy things to do would be go to a stabilized control lens with an O-ring in it to guarantee everything. That's not always required. You want to make sure that you get the product that is commensurate to the application need to make sure you get the best price and product performance for your system. And with that, I think we have a few questions that have come in that we'd like to entertain at this point.
Yeah, Greg, first off, thank you so much for your time. We had a couple questions. A lot of them were already answered offline with our engineers. Two of them were notable, and I wanted you to answer them for everybody. Number one, do these lenses have better beam pointing than the standard line of products?
So the beam pointing accuracy of the optics is inherent to the mechanical design of the optics themselves. What you're adding to here is the actual gluing and tacking down of the optics into the barrel. So the inherent beam pointing accuracy is part of the design itself. What you're guaranteeing is the repeatability of that beam pointing over time.
I see. Second question, I thought this one was interesting. Somebody wrote, I have a lens already. Can you ruggedize my lens for me?
So that is theoretically possible, but the amount of rework that would have to be done, the potential damage could create issues. Our recommendation at that point is to see if there's something that already exists that might be ruggedized, or if you're going to volume, it could potentially be rolled over to that. But there's a fair amount of these products available on the shelf that are already done for this, and it'd probably be the easiest way to handle it.
Thanks, Greg. That covers all the general questions. Thank you, everyone, for your participation. We really do appreciate you being here. Just as a reminder, a link to today's recording will be sent out to all participants shortly. And for more information, please visit our website at www.edmundoptics.com/ruggedized. Thanks again for joining us today, and we look forward to seeing you again next time.